All right, so we're going to do radical reactions. What is a radical? Anybody know? Anybody know the official definition? Yeah, with an odd, they call it an odd electron. It's not paired. So anything, hang on. For example, that would be a radical, right? Hydrogen radical. Chlorine radical would look like this. Right? It just has an odd electron, unpaired electron. So that's what we mean by radical. Sometimes there are diradicals. Those can actually have an even number of electrons, but there's two unpaired electrons in that case. So radical simply means unpaired electron. So, what do you think about reactivity? You've got an unpaired electron. Yes. Less reactive, more reactive? More reactive, because electrons like to be paired. Generally, things don't, when they're radicals, don't have their octet.
Well, it's unstable, right?
So it's unstable, right? So it wants to be stable, and so that's sort of the point. Okay, so these are the reactions that we're going to be covering. Okay, so we're going to do substitution. I may talk about antioxidation. I find that to be not a very interesting topic, although a lot of people seem to think it's really cool. And then we're going to talk about addition reactions. So if you remember what a substitution reaction is, right? You take one thing and you substitute with something else. And the most common substitution mechanism that people usually know or learn from the first semester is like SN1 and SN2, right? Substitution, unimolecular, bimolecular. Of alkyl halides and alcohols. So you have some nucleophile comes in and pushes another group off. In radical reactions, we're typically talking about substitutions of hydrocarbons. So things that don't really have functional groups or alkenes or alkynes. Okay? So yeah, in substitution that we're talking about, we're going to be looking at, for example, CH3 with a halogen and then ending up with an alkyl halide. So that's typically the kind of substitution reaction. It looks pretty messy. That's typically the kind of substitution reaction that we're talking about. Now, we can also do addition reactions. Right? And we talked about addition reactions last semester using peroxide with bromine and getting the anti-Markovnikov addition. And so what we're going to be doing is talking about how we get the anti-Markovnikov addition of HBr. We'll actually look at the mechanism this semester. So we can have addition reactions as the most common addition reaction that you're used to seeing from first semester are like electrophilic additions to alkenes and alkynes, where an electrophile pulls and breaks a pi bond and then adds to both sides. So what we're going to be talking about is what happens and why is it different when you have the presence of peroxide. And it turns out it's a radical reaction mechanism, so we'll get into that. Allylic substitutions we set off by themselves as well. If you remember what allylic means, let me just do a little bit of a refresher. Allylic substitution would be something like this. And you know there's a lot of hydrogens on there, right? So there's hydrogens here, there's hydrogens there, there's another hydrogen here. But when you have allylic substitution, or actually benzylic substitution, what you tend to get, oops, I started doing benzylic all of a sudden. Substitution primarily occurs at that position. So we'll talk about how that happens. And the reagent that's really important for this is called NBS, and we'll go into what all that is later. Okay, so that's kind of the outline of what we're covering. So then the question is, how do radicals form? Okay, so there's a couple of ways that we form radicals. First of all, Radicals are really reactive, and so once you form a radical, they tend to form more radicals, okay? They tend to, because they have an odd number of electrons and are unhappy, when they react, they tend to take one electron from something, leaving one electron behind, and so you end up always generating more radicals from radicals, okay? So there's a term, we saw homolytic and there's heterolytic cleavage, and when we talk about homolytic cleavage, what we mean is one electron from the bond, okay, that's connecting two species like X and Y, one electron from each species. Great, say it froze. Yeah.
Just curious, are you going over 11 because last semester you didn't get to cover it?
Yeah,
okay.
yeah. Yeah, so you guys got 11.
Yeah, we got 11.
I fit it in,
All right.
and this last semester I
Yeah,
didn't.
I was talking to some of your students, and they're like, no, we didn't go over 11.
Yeah. Yeah, so it'll be a little review for some of you guys, which is good. This is good. It helps me make the transition back in a little easier. Since you guys were forced to take the semester off?
Yeah, I was going reviewing, and this is the only one I didn't cover review again.
Oh, okay. So for a radical, when you do what's called homolytic cleavage, so here's a question. Why does one electron go the one way and one electron go the other way? Because what you're used to seeing is what is known as heterolytic cleavage. So for example, if I had, oops, I did it again. If I had this, let me just draw it up in the corner. What maybe you're used to seeing, man, it's really slow, is this. And really, I shouldn't do it at primary. I should do it as a secondary, right? So I'll cheat. I'll fix my drawing. All right, that's the E or E1 or the SN1 mechanism. When you form a carbocation first, you get what we call heterolytic cleavage. What's the difference? Why would that be heterolytic cleavage? What would cause homolytic cleavage? Right. Why do both electrons go with the chlorine?
Because it's forming an ion.
Forming an ion, but why is it going with the chlorine and not with the carbon? Yeah, it's the electronegativity, okay? So when you have things with different electronegativity and the bond breaks, right, and that's always an endothermic process, just reviewing a little bit, but it always absorbs energy. When the bond breaks, it breaks in such a way that the electrons typically go with the species that's more electronegative. But if X and Y have like the same electronegativity or very close electronegativity, when the bond breaks, it tends to be homolytic. That is, one electron goes with one electron goes with the other. So when we draw the arrow for this is one of those nitpicky things that you have to practice and be patient and take time to draw your mechanisms. 2 electrons, the arrow has 2 barbs on it, okay? And 1 electron, the arrow has 1 barb on it. And those are often, like when you read in the book, and they're called fish hooks because, you know, like a fish hook has a barb on one side. So they call them fish hooks. Okay, so draw the arrows for these. So for Cl2, when the bond breaks, H nu or HV, what's HV? No, it's not H. That's not heat. It's light, right? It's Planck's constant times the frequency, and that's just for. You know, how do you abbreviate light on a reaction arrow? It's usually H nu, right? We don't draw a squiggly line like the arrow, the wave of light. We usually write H nu. So this represents light. Oh, great. It's very slow. And when that bond breaks, 1 electron has to go to one direction, and then 1 electron has to go the other direction. So you do it like that, right? When they get together, like if this was an equilibrium process, in some ways it is an equilibrium process, right? The 2 Cl's, you have to make a sigma bond, right? So if I was going this way, maybe I'll use a different color. don't know what color this is, but when I go this way, can you see that? Yeah, it's okay. Then what do I have to do? I have to form a single bond, right? For one electron from one side, one electron from the other. So what you do is you take something like this, and they just meet in the space in between so that they pair up in between the two to form the bond. A little bit foreign. Any questions?
Can you do that with heat?
Yeah, and you can do it with heat too. Yeah. So heat or light are typically what are used to dissociate the bond between. Sometimes you form another radical, which causes the formation of the radical. But in this particular one, it's usually light or heat. Okay, so what's the one? So that was top one was homolytic, right? What's the next one look like? Yeah. So then you're going to go to break that bond. Which way do the electrons have to go? They have to go towards the chlorine. So start the remember the reaction arrow starts at the bond. Is it that the right arrow?
No.
No, it's got to have two, right? So there'd be like that. And then you would end up on the right. And then if you're going to go backwards, you would start at the electrons and then probably go to the carbon.
It's just a nucleophile attack, right?
Yeah, that's a nucleophilic attack on a carbocation. Yeah. Okay, try to figure out what the next one is. Don't worry about homolytic or heterolytic. Sometimes we get a little bit too caught up in that kind of stuff. But what happened in that bottom one? Did this suddenly appear? We spontaneously generated a hydrogen? What's missing on the structure on the left that's on over here? It's the hydrogen, right? Where did it come from?
It's split from the ethyl.
From the ethyl group, right where it's attached to the benzene. So this is known as the benzylic carbon. So it has to be on the benzylic carbons. We'll go back and we'll draw that. And this is one of those principles, radicals tend to form more radicals. Oops, let me change my color again here. Okay, so now, the electron flow, right? The oxygen is attaching to the hydrogen, so it attacks the hydrogen. But remember, it's making a sigma bond between here and here. So that means this has to come up and attack the hydrogen, but you can't go all the way to the hydrogen. You have to meet it in space. It has to come part way through. So we're going to come like this. And then this bond is going to break like that. Now, when doing radical reactions, anytime you break a bond, you have to say what happens to both electrons. Okay? So that means this has to go back. So every bond that breaks in a radical reaction, there should be two arrows on it. One going to wherever that radical is going towards, and one going back to the atom that's essentially left behind. Okay. If you're going to try to do this as an equilibrium, draw this as the going backwards, you really need to have another hydrogen drawn out here. One-sided, one-sided. That's how you would go back. Okay. You have to draw the bond in. These slides weren't meant to have that done, so we're just kind of fidgeting on them, fudging the slide a little bit. So we good? Break a bond, right? When you break a bond, radical reactions, always two arrows. When you form a bond, like a sigma bond, then two arrows have to meet in space somewhere, right? Okay, so let's talk a little bit about the structure of a radical. We know carbocations are sp2 hybridized. sp2 hybridized, unoccupied p orbital, flat, right? So it's planar. And we know that carbanions, which we studied last semester a little bit, carbanions are sp3 because we have a filled orbital, right? So a radical is, at least on starting with an sp3 carbon, for example, is halfway in between those two, right? So the question is it sp2 or is it sp3? And it turns it's like sp2.5. It's like halfway in between, okay? Which is interesting because I don't know if you remember some of this stuff because we didn't cover it too much, but structures like this can undergo inversion. Right, so that means the lone pair, the way we draw it up here, can actually penetrate through because it's in the orbital and be on this side, and you can get the umbrella flipping like this. So you can have inversion. So essentially, when you have a radical, it inverts very easily because there's less electron repulsion. It's easier for it to go back and forth, and less strain for this inversion to take place. What you looking for? You're looking for social sciences, maybe? SO? It says music speech. This is MSc. Yeah. That one. Yeah, we have too many science buildings. We have health science. We have social science.
And the real science.
And then we have our science, the real science. And then we have buildings that sound like they should be math science. They're the music speech buildings. And then anyways. About 10, 20% of the questions I answer every semester, the answer is, oh, that's the wrong building. And then I try to find a map. Have you tried to find a map on our website of the campus? You pull one up, and it's tiny. You can't see anything. Ugh. Okay, so somewhere between sp2, sp3, but they're very reactive because they have the unpaired electron, right? So think about what that means. For stability, let's talk about stability. If you have a carbocation, which carbocations are the most stable? Tertiary and ones with resonance delocalization of charge, right? So those tend to be, so allylic carbocations, next to a double bond, or tertiary carbocations, or benzylic carbocations, those tend to be the most stable. And the reason is because the groups that are around the carbocation donate electron densities sort of help satisfy the missing electron, right, the deficit that it has at that carbon. We call that, you guys remember the word? Hyperconjugation. We call it hyperconjugation. So that's the thing that we talk about. Hyperconjugation donates electron density. Same effect here. Okay? Not as dramatic because it has one more electron than the carbocation, right? Still reactive, but still you're able to stabilize it by having more groups around the around the radical. Okay? You could think of it as intervention. Okay. Hydrogen, no intervention, not very stable. All right. Tertiary, much more stable. These guys all can donate electron density to help stabilize the deficit of the electron on that radical. So it follows exactly the same trend that we see in carbocations. It's just not as dramatically different. Okay? And that makes a big difference because in carbocations, one of the things we always have to worry about is rearrangement. We don't see as much rearrangement with radical reactions. Okay? Not the kind of hydride shift thing that we saw in carbocations. Now, if you guys remember, you do calculations of energy using energies of reactions using bond energies. And so one of the things that they measure is bond dissociation energies. And we didn't really talk about this, but when we're doing bond dissociation, so let's say, oh, I have a C, oops, pick a different color, not that that's a bad color, CH3H, and then I'm breaking that bond, and I get CH3 dot plus H dot. Those are the bond. That's what the bond energies we talk about in all those tables from Chem 1A in first semester organic chemistry. They're actually talking about the formation of radicals. How much energy does it take to form the radical by doing the cleavage where one electron goes one way and one goes the other? So if you measure the bond energies for methane, which is that one up there, right, or ethane, or propane, or T-butane, I guess this would be. What would you call that? I guess T-butane, yeah. Look at the dissociation energies. The dissociation energies start at 105 and go down to 97. So that's the easiest, 97 is the easiest bond to break. If you think about the energy diagram for the process that I drew up there, we're looking at the formation. This is the radical. This is the reactant. So for formation of the radicals, you break a bond, so it's endothermic. So the radicals are less stable, so it goes up in energy, right? It takes less energy to break this bond than it does to break that bond. Why is that important? Because when you do a radical substitution reaction, you have to form a radical, right? It's going to give regiospecificity to the reaction. Right? Wherever the radical forms that's the most stable is the one that'll give the major product. Okay? So this, again, repeat, which the reason knowing about bond dissociation energy is important, right, is the most stable radical, okay, will lead generally to the major product of the reaction. So it's important to know, like, what's the trend in stability when you're doing radical reactions. Same thing's true for substitution, carbocation reactions too, right? Before we get into the first mechanisms, we should cover resonance structures. I think it should be fairly clear just from what we drew earlier. You'll notice that down in here, this is an allylic radical, and when you do a resonance structure, right, two arrows have to meet in space, right? So this electron will move over here. Oops. That electron will move there, but you got to get another electron to it, and that electron comes from this pi bond. A lot of times you'll find there's not enough space to draw it, and there's some general like aesthetic rules. I mean, it's okay if your arrow goes like this, just because you can't, like if you're fat-fingered like I am, can't get it all in there, okay? And then you're breaking a bond, right? So when you break a bond, you always have two arrows when you break a bond, one going towards the bond and one going away to the atom that's sort of left out of the process. So this is the resonance structure. If you wanted to go back, that is going in this direction, you would most likely then go something like this. And like I said, you know, you should probably try to not cross bonds like that, but sometimes it's just impossible otherwise, just to fit it in. Especially on exams, I give you a little tiny structure that I meant to draw like this big, but instead I drew it that big. And I'm like, oh, sorry guys. You'll deal with it. All right. How do you think resonance affects the stability of a radical? Stabilizes it, right? And actually makes it more stable. And it probably is one of the biggest factors in determining stability of radicals, because the radicals at primary, secondary, tertiary aren't as different as they are in carbocations. Okay. So let's go ahead and do a little practice. Try to draw the resonance contributors or the resonance structures, and then we'll try to draw the hybrid for this and the one that was on the previous. I'm going to draw it too, but don't pay attention to me. Where there's a couple of them actually. right, I didn't leave myself room to draw my arrows. Ah. Well, that looks crazy. You get that? And, just to make note, these are almost identical. They're almost identical except for the position of the pi bonds in the benzene ring, but you know how those alternate? Okay. So you could draw the whole next series and shift the electrons all the way back. You know, if I asked you to draw this one, just draw these structures and then you know, sorry. You can draw this one. Oops, sorry, it's not there. And then these are in resonance with each other. And that's just the pi bonds rotating around on the inside. All right, you don't have to go through, because you can actually bring the radical back in here, then break the pi bond and go here. And then if you go all the way back around the circle again, right, you'll get back to the original structure. Okay, what's the hybrid look like for this? Now, if it was a cation, it'd be easy. You put a positive charge in the middle. If it's an anion, it's easy. You put a negative charge in the middle. In a radical, what they tend to do is draw it like this, dot, 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 and then dot, 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 like that, and then they put a dot in the middle, which my program's not letting me do because it thinks I'm trying to select something. All right. So you basically, what I'm trying to draw on there, which, because the stylus doesn't let me. Like that, and then I usually put a dot. The dot represents it's a radical, right? If it's a neutral, that's implied, but they usually put a dot in the middle. If you look at this one before, all right, and oops, it would just be something like this, and a dot. So it's a radical electron distributed through the pi system on that structure. Okay. All right. And just to make some extra notes here, this is the, your book, I don't think does this part clearly. Benzylic and allylic radicals, the ones that are at the top, are the most stable. The trend follows carbocation stabilities going the rest of the way. And this is a vinyl, right, radical. Vinyl radicals are very unstable, okay? So vinyl means the radical is directly attached to the carbon with the pi bond. Allylic means it's attached to a carbon next to the pi bonds. Allylic tends to be very stable. Vinyl tends to be very unstable. Questions? I'm going to have a suggestion box, actually. I have to build it. I could probably buy one, but I'm going to build it. And it's a technique. I spent 3 hours or 4 hours on last Thursday in a meeting in the morning. And I learned one thing. So the one thing, though, is it's called the muddiest point, and it's also combined with this thing called the 1-minute essay. And so I'm going to ask that at the end of every class that you write down 1 or 2 sentences, the 1-minute essay, on the thing that was least clear to you, so that when I come back in the next class period, I can answer it. Because some students don't want to say something in class, or some people don't want to stop the flow of the class because it's probably not that important. But when I hit that point and you're like, I don't understand, just write it down. I'll put it in a box. I won't answer all of them, but the ones that are the most common, those are the ones I'll answer. Also, if there's something like you want to know, like how is this used in biomedical research? I might have an answer, might not. If I do, and it's an interesting question, I'll just, at the next class, I'll just bring it up, okay? And we'll spend about 5 or 10 minutes going over those questions to get some extra clarification, or I will write something and post it on Blackboard or OneDrive so that you have a document saying, oh, this is why this is important, or this is how this happens. This is the mechanism drawn out for this structure, okay? I'm still recording. It stopped for a while, sorry. So, just to make a note, radical formation is favored by resonance stabilization more than it's favored by degree of substitution. First note. So when we're doing substitution reactions, and that's the second half of the substitution reactions, substitution almost always takes place at those positions. Okay? Because those are the easiest, the stability is the greatest, so those bonds are the easiest to break. And I guess it was important enough I made my own slide just for those 2 structures, right? Which is the benzylic, right? These are the benzylic ones, and these are all allylic. Okay, so let's go over our first reaction mechanism of the semester. I know we all want to celebrate, but we should probably work instead. Maybe I just want to celebrate. We're going to talk about how radical substitution takes place with a halogen and a alkane. So just to be clear on the type of reaction we're talking about, I'll just give an example one. CH3, CH2, CH2, CH3. I'm going to do radical substitution, which means I'm going to do Cl2 or Br2 or F2, okay? On the arrow, I'm going to do heat or light. So that's light. That would be heat. I guess you could do both. I don't think it matters. Usually only see one. And the substitution reaction is one of the chlorines from the Cl2 will substitute for one of the hydrogens. Okay. Okay, so based on structure and stability of radicals, where do you think most of the substitution will take place?
Can you repeat that?
Based on stability of radicals, where do you think most of the substitution will? Yeah, inside. That's typically the most inside position is where substitution will take place. So if you have a secondary versus a primary, it's going to be secondary. If you have a secondary versus a tertiary, usually it's tertiary. Okay. It's a little bit trickier than that. He'll talk about like the distribution. Actually, you can calculate the product distributions in radical substitution reactions, like to within a few percent, just using a calculator and some numbers. And it's kind of cool, so we're going to do it. Your book doesn't do it. We're going to do it. Yeah, so your product is going to be something like that. That'll be your major product, most likely. Okay, without doing any calculations, probably your major product. And then what's the other product? HCl. Okay, so thinking about what has to happen, we have to have a radical that's formed initially. Okay, once the radical's formed, right, that radical will produce more radicals. And it turns out it does it in such a way that radicals that produce more radicals, that produce more radicals, that produce more radicals. So it's like a chain reaction, okay? It's often called radical chain reactions, but it's a chain reaction. And they call that process where the radicals keep generating, we call that the propagation phase, okay? So we have an initiation phase. So the light is only exposed for a very brief amount of time. The light in this case is going to be used to cleave the Cl2 bond, okay, the Cl-Cl bond. And then once you've done the initiation, the Cl bond will go through the process of doing what's called hydrogen abstraction. So Cl radical will pull a hydrogen off of the alkane. So abstract a hydrogen from the alkane or pull it off. Okay? And then it turns out that's going to cause the formation of another radical, and you'll get a halide abstraction. That's the Cl2. So something's going to pull a Cl off. And then when it does that, it turns out it makes another Cl radical. Okay, so I'm going to draw all that out. Okay, it's all on the next slide. The last bit is what they call the termination phase. Okay, and the termination phase is when you run out of reactant and there's nothing to pull and form new radicals with, the radicals that are left sort of just recombine, right, and form stable products or byproducts. Okay. I often make the analogy of like going to UC Berkeley. Now I went to Santa Cruz, and when I went to Santa Cruz, it was just like this love-hate relationship with Berkeley. So like when Santa Cruz professors make jokes about things they don't like, it usually, at least when I went there, usually included somebody from Berkeley. Okay, so I use Berkeley still in my examples kind of because of that. So when you go to Berkeley, the first thing they do is they initiate you. So you get initiated, they form a radical out of you. Okay? And then you go through the whole system, like freshman, sophomore, junior, senior year. You're going through all this radical propagation. You keep generating more radicals as you go along. And then you graduate. And then what happens? Well, you know that when people graduate, they tend to become more and more conservative. Right? So then the radicals are like, oh, there's nothing left to react with. So they start combining. And because they found some stability, they're like, oh yeah, that's it. I'm not doing that anymore. I'll just donate money to the school, or I'm not going to go stand out on the street naked. Because, you know, that stuff happens. It's always fun going through Berkeley. And you never know when you'll run into naked bodies. When I was at Santa Cruz, it wasn't much better, actually. There was a friend of mine who told a story about how her sort of perspective really changed when she was jogging in the forest, and her physics professor came jogging past her in his tennis shoes. In his tennis shoes. Nothing else. He's just out in the forest at Santa Cruz jogging naked. He had his feet covered. He was like, yeah, that was a life-changing moment. I'm like, yeah, that would change my life too, I think. So yeah, there's some weirdos at Santa Cruz too. He was, by the way, a very good professor. And I would recommend him if he was still there and not jogging naked. I don't know. I might still recommend him. It was pretty fun. Yeah. So let's talk about the initiation step. Initiation step is the formation of the initial radical. And what you'll notice about all of these radical initiators or radicals that are formed, the initial radicals that are formed, it's generally between two atoms of the same type. Okay? So you have a Cl bond, you have a peroxide bond, which we've talked about being generally unstable. Those are very common things that we use to generate the initial radical in a reaction. And these peroxy radicals, what do I want to call this? Peroxy ester radical, maybe? Yeah, that might be the right word for it. Oh, they call it an acyl peroxide. Anyways, when you break this bond, this one's really easy to break because it has resonance. Right? It can delocalize this radical over to this oxygen. So all you have to do in the initiation step is form that radical, and then you could turn the laser off or the heat off. It doesn't have to be on during the process. Okay. One of the things they make note of is that on the acyl peroxide, you could heat it up to 80 degrees Celsius and that'll initiate the reaction. Okay? A lot of these reactions are exothermic, though, so you have to be really careful about heating things like this up because they're going to get hot all on their own. Okay. So here's the example question. Show the initiation, propagation, and termination steps for the monochlorination of cyclohexane. Okay. So what is that going to look like? Let's draw the reaction before we get started, and then we'll do the mechanism. I have the mechanisms all drawn out for you. We'll talk through it. You might want to just get ready to take a picture of it or download it or whatever you're going to do. So there's cyclohexane plus, all right. What am I adding? Chlorination, so Cl2. I might use a radical initiator that is something besides Cl2, or I might just use light. So I'm going to use light. And then what will happen is you'll form a substitution product. These are all secondary, so it doesn't really matter which one you put it on, plus HCl. Okay, so that's the overall reaction. So now what we have to do is we have to go through the steps of the reaction. Now, the first step is the formation of the radicals, so we'll start with Cl2. And actually, it's on top there. I'll draw it out for you. It's pretty simple, though. And that forms 2 Cl radicals. Like that. So that Cl radical, so that's the initiation part. Sometimes the initiation part is more complicated. Sometimes it's easy. You break one bond. Okay, you only do that once in the mechanism. And then what happens is that radical, that shows up down here. This is known as the hydrogen abstraction part. It's unstable. It runs into an alkyl halide, which presumably because it's the reactant you have a lot of in there. And that radical then finds and bonds with the hydrogen. So this, yeah, do it like this. That's going to be the HCl, right? And then the cyclohexane becomes the cyclohexyl radical. There. That's the electron that's left after this step here. So this is the hydrogen abstraction step to form the cyclohexyl radical. If it's more comfortable for you to draw it as 2 steps, then you can draw it as 2 steps, because then the next thing you'll have is down here, you have the cyclohexyl radical. And that's going to react with Cl2. And then you would draw Cl2 with the bond like this. Okay. And then the radical is going to attack the chlorine, and then it'll do something like that. So the product of that is actually the product of the reaction. It's chlorohexane. Yeah. Plus what else? The radical, the chlorine radical. Okay, now that you have the chlorine radical, right, that's this guy here, where else do you find him in the reaction? You find him in the very first step. So that as long as there's cyclohexane present, reactant present, that's the dominant reaction. It just, the chlorine radical comes out, he forms, there's more cyclohexane available, so it reacts to form more product or more radical, and then the cyclohexane, right, radical, cyclohexyl radical, combines with the Cl2. Now, you might be saying, well, how come this doesn't react with this? Right? It does. If it does that, though, what does it form? It forms Cl2 and a Cl radical, so it comes out being the same. And we just don't repeat that process over and over again. So the Cl radical might react with this to form a Cl2 and a Cl radical, but you still have a Cl radical available. And as long as this is there, it will react with it. Okay? So you notice this is the propagation, because what you're starting with to make the reaction start, the Cl radical ends up being one of the products in the propagation step. That's almost always the way it is.
So just the location of the unpaired radical is just moved, right?
Yeah. You always have, when you have a radical reaction, you're always going to have this one radical somewhere in the process until you run out of reactant or the reaction concentration runs low, and then Cl radicals become dominant, and then they just recombine with, they terminate with each other, yeah. So the termination steps, I mean, could look like this. Two cyclohexyl radicals get together because the Cl radicals can't find them, or the Cl radical and the cyclohexyl radical get together. So the propagation process is pretty straightforward. Termination step usually ends up in a bunch of minor products. Okay? And then you purify all that stuff out. Plus, you also get some more of your product that way, too. On exams, I typically will do one of two things. I'll say, draw one or two of the termination products. One could actually be the product, because it is one of the termination products. And then one is usually one of the reactants or something, and show the mechanism. Or I might say, could this be one of the termination products for the reaction? And you have to explain why it is or why it isn't. Okay. So I would draw a structure, right? And you'd have to like tell me whether or not it could be one of the likely products. Okay, so these reactions are regioselective. It's already mentioned this a couple of times. There's usually a preferred major product. Now, when we talked about substitution reactions or addition reactions, the regioselectivity was based strictly on, what we talked about was strictly stability based. Which is the most stable carbocation? That determines the regiospecificity. Which is the most stable alkene, double bond, pi bond? That's that stability determined regioselectivity. Location of the leaving group, the type of, all these things determine. And in radical reactions, it's predominantly determined by kinetics. How fast the reaction takes place. Okay? And so that's determined by two things: the relative rate at which the substitution takes place, and by the number of hydrogens that are present of that type. Okay? So think about that. The number of hydrogens of a type and the relative rates of reaction will determine how much product of that type gets formed. So let me set this up for you. Let me just draw a molecule, and we'll talk about it. Okay, so here's CH3 butane, right? And if you count the hydrogens on butane, how many methyl hydrogens are there? Methyl hydrogens. There's two methyl groups, right? So 6. All right, 2 methyl groups times 3, 6 methyl hydrogens. Right? So this should be 6 primary hydrogens. I don't know where 6 tertiary carbons came from, just completely wrong. Okay? And then there's, I don't know, I just like, you know, that's probably been on my slides for like 2 years. Sorry. But there's 6 primary hydrogens, and there's 4 secondary hydrogens. So if you're just strictly going on statistics, that's 10 hydrogens, right? 60%, if it was just statistics, 60% should be primary, right? 40% should be secondary. And you would expect the product breakdown to look something like this, if that was all that it was. But as it turns out, the rates of reactions have to do some with stability, has to do with the stability of the radical, though. So we know tertiary is more stable than secondary is more stable than primary. So the relative rates of those reactions are all different, where tertiaries are faster than primaries. And so what they usually do is they say, well, if a primary has a rate of 1, just arbitrary, no units, has a relative rate of 1, secondaries are 3.8 times faster, tertiaries are 5 times faster. And that's based on stability of the radical that's formed when the hydrogen abstraction takes place. Okay? There's some other factors, and we'll talk about that too, but it's more detail I want to get to. So in the next couple of slides we'll talk about it. So what does the actual percentage end up being like? The actual percentage ends up being like this. That is, the secondary substitution is 71% of the product, simply because secondaries are so much faster than primaries. But it's a combination of the number of hydrogens and the rate of the reaction of those hydrogens. So let's practice. Let me do something on the board here. All right, actually, you know what? I will do this. I haven't done this in a while. Well, actually, never mind. I'll just use the one I have. I'll just draw on this slide. So let's figure out how we do this calculation. I'm going to show you rather than tell you, because if I tell you, it's going to be like blah, 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 multiply, blah, 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 add, blah, 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 divide, blah, 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 convert to percent. And you'll be like, okay, he said something. I'm not going to say it. I'm just going to show you. First, you have to figure out how many of each kind of hydrogen there are. Ignore this dot. That's part of the sigma bond that's going between these two carbons, which I can push together close enough so it didn't hide it. Okay. So ignore that dot. But ignoring that dot, how many primary hydrogens do I have? A bunch, right? There's these, there's these, there's these. So I have 12, right? So I have 12 primary. How many secondaries do I have? 4. And then how many tertiaries? 2. Okay. Now the relative rates of each one of these, primaries are 1, right? Secondaries are 3.8 times, and tertiaries are 5 times. So in order to calculate the total probability, if you want to call it that, right? The total, you just take 12 times 1, 4 times 3.8, and 2 times 5. And you add all that up. That's actually what's shown in this step here. There's 12 times 1, that gives me 12. 4 times 3.8, so that's 15.2. And then 2 times 5, and that's 10. You add all that up, it's 37.2. That's the total of all the probabilities added together. Okay? And then the relative percentages of each product, you just divide the probabilities of each by the total.
Can you go back?
No. To what it, yeah, that one.
So those two tertiaries.
Yeah, so there's these 2 tertiaries,
CH, yeah.
and then these 4 secondaries, and then there's 1, 2, 3, 4 methyl groups. All right, so there's 12 there. And you're going to take and end up multiplying, right, 12 times that, and then 4 times that, and then 2 times that. And then adding all that together, you think of that as the total cumulative probability of that whole thing. Okay. That's the 100%. Okay. So now that's what this is. And then you just calculate percentages, and this tells you that you have 32% of the primary, 41% of the secondaries, and 27% of the tertiaries. Now, secondaries ended up being more than the tertiaries because there's twice as many secondaries, okay? Now, if the molecule's asymmetric, you could still do the calculation this way, but then the percentage of each product is based on, again, the percentage of each type of hydrogen, right? So if it's asymmetric, you have to do a few more calculations, but you can figure that out.
So the numbers that we were multiplying, those came from.
Just experiments, yeah. Empirical observation. Okay, yeah, so first step, identify your hydrogen. Second step, multiply the probabilities. Third step, calculate the percentages. That's how it's done. Probably have you do one of these, okay? I may not have you actually do the calculation, just show that you could set it up and know how these numbers work. So what are those actual products? Well, primary substitution products, this is molecule symmetric, right? The CL could be here, 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 or here, doesn't matter. It's one of them is all the same. Secondaries are these, and tertiaries are these. So the CL could be here or it could be here. Secondary, the CL could be here or here, and then you swap the hydrogens, number of hydrogens. Okay. I ran out of time. Bummer. Good place to stop, though. We'll pause here, and we'll continue on Thursday.